Bismillahirrahmanirrahim. Dear students, I will start lecture number 2 for week 12. We will discuss two important things in this, two important concepts in this lecture. First is the expected values and obviously then the variance of continuous random variables. And then I'll go on to discuss two useful continuous random variables, families of continuous random variables. So first, the expected values. What we mean by expected values and how we can express the expected value for continuous random variables. So the first topic of today's lecture is expected values. If you recall, the expected value for any random variable x, if x was a discrete random variable, we used to write it as the summation on all the possible values of this random variable x, the value of that random variable times the probability of the same value. Then you multiply it, you get one product, then you take another value of x, you multiply it with the probability of that value of x, and similarly you sum up all those products. This was in the case of discrete random variable, but now we are discussing continuous random variable. So expected value of x, if x is a continuous random variable, can be very easily written if we know this formula. You know, the summations will be replaced by the integrals and the PMF will be replaced by the PDF of the random variable. So now we write it as such. Integral from minus infinity to plus infinity, these limits are there to cover all the possibilities. X times the PDF of this random variable x, and obviously the dx. So now we see how we write the expectation. You simply take the value of a random variable x. In fact, this is the functional form then, and then you multiply it with the PDF of this random variable, and then you integrate it for all the values. Okay. Always remember, a function of a continuous random variable is also a random variable, but this function may or may not be continuous. This is another extension to the concepts of continuous random variables. A function of a continuous random variable is always a random variable. However, this derived random variable or this function of the continuous random variable may or may not be continuous. Please keep this in mind. And if we have, if we want to have the expectation of a function of a random variable, we can write it as given in the form of a theorem in your textbook. The expected value of a function g of x of a random variable x is written as expectation of g of x, and you know the philosophy of how to write the expectation. It is simple. You integrate on all the possible range, then it is the functional form, and then the PDF of the random variable x dx. So this is how you find the expectation of x, which is one special case of this, and this is how you find the expected value of a continuous random variable. So if this is known, you should be able to write the formula for the variance of a continuous random variable. So let me now write the formula for variance of a continuous random variable. So the variance of x, if x is a continuous random variable, is nothing but the expectation of x minus the mean whole squared. And you know how to open the expectation. When you break this expectation sign, and three things will emerge: the integral, this thing, and then obviously the PDF of the random variable x. So you can easily write the complete formula for this variance of x. So we write it as such: integral minus infinity to plus infinity. We have broken this expectation sign, so three things will emerge. One is the integral sign, the other is whatever is in the argument, which is now x minus the mean of x whole square, and then you multiply it with the PDF, which is f sub x of x, and we have dx because of the integral. So this is how you find the variance of a continuous random variable, and this is how you find the expectation of a continuous random variable. A few important formulas that I'll write now, which are applicable to both the discrete random variables and the continuous random variables, and this is also given as a theorem in your textbook, and that says for a random variable x with mean mu x, sometimes you write it as mu expectation of x, and variance of x as the expectation of x minus mu x whole square, we have the following. First, expectation of x minus mu sub x is always equal to 0. I don't even need to prove this because we have done this in the case of discrete random variables as well. So the average spread of a random variable from its mean value is always equal to 0. This is the understanding that can be extracted from this expression. The average, the expected spread of random variable x from its mean value is always equal to 0. Second important point to be remembered is expectation of ax plus b, which means the expectation of a random variable x which is scaled by a and shifted by b is simply a times expectation of x plus b, which means the average, the expectation is automatically scaled with a. C, already known to you, variance of a random variable can be obtained by this simpler formula: expectation of x square minus expectation square of x, which is mean of square minus square of the mean. This is again known to you. One more important point: if x always takes a value, a constant value, then its variance is 0. Now, one more point: if we have y as some shifted version of a continuous random variable x, if y is equal to the x plus b, then variance of y will be simply equal to variance of x, which means shifting does not affect the variance. But this is not the case when we have a scaled version of x. So now if you have a derived random variable y as a scaled version of the parent random variable x, then the variance of this derived random variable is a square times variance of x. So if you see these two relations together, you will note that if you shift a random variable by b and obtain a new random variable, a derived random variable y, the variance of y is exactly equal to the variance of x. But if you scale a random variable x with some number a, then the variance of this derived random variable is equal to a square times variance of x. So the magnitude of variance will depend on the of the scalar. These are a few important points about the expectation and variance and some related formulas for continuous random variables. Always remember, you can always easily extract or recall the formula of the expectation of a continuous random variable if you have in your mind the formula for expectation of a discrete random variable. The expectation of a discrete random variable is simply summation sign, the value of the random variable and the probability of this value. So you keep on multiplying these two things for all the values of x, and then you sum up all those products and you get the average value of the random variable or the expected value of the random variable. And as I told you in the last lecture, that when conceptually going from discrete to continuous, summations will be replaced by integral. So you see, for the expectation of continuous random variable x, the summation is replaced by an integral. This stays the same, and then this PMF is replaced by the PDF, and obviously dx has to be there because of the integral sign. So this is how we find the expectation, and this is how we find the variance of a continuous random variable. And then we discussed all these points. This is already known. The measure of average spread of a random variable about its mean value is 0. If you scale and shift a random variable, only scalar will affect the expectation and not the shifting. A variance of x is equal to expectation of x square minus e square of x, which is again simple to remember. If you shift a random variable, then variance of y will be equal to variance of x. But if you scale a random variable x with some scalar a and you obtain a new variable y, then the variance of y will be a square times variance of x. So it depends what the value of the scalar is, and then it will give you the value through this formula. It will give you the value of the variance, the magnitude of the variance of the derived random variable y. Now I'll do an example, a simple example on how to in fact, I'll do the example a little later. First, I'll go through two families of continuous random variables. So the next topic is some useful continuous random variables, the families of continuous random variables. If you recall, in the discrete case, we discussed 5 different families of discrete random variables. But in the continuous case, we'll discuss just 3 of the most important families of continuous random variables. So the topic is some useful continuous random variables. So the first of the families that we'll discuss here is uniform random variable. If you recall, we also had a discrete uniform random variable, and the concept there was that each value of that discrete uniform random variable had the same probability. Now, if you convert that concept into a continuous form, it means you have the random variable x, and then you have the PDF of the random variable, and then you have, say, this area in terms of probability, and the continuous uniform random variable basically means that if you take all this interval and say you divide it by 2, then half of the probability will be in this interval and half of the probability will be in this interval. In this particular case, you have uniformly distributed the probability among 2 equal sized intervals. Now, if you divide this whole interval, say from 0 to x1, into 4 parts, this is again a uniformly distributed continuous random variable, and it means that the probability of each interval is equal to the probability of any other interval of the same size. This is important. Any other interval of the same size. So here now each interval will have a 1/4 probability. But if you further, for example, divide the total interval into, say, 8 equal size intervals, then the probability of each interval will be 1/8. So continuous uniform random variable now means that if you can divide the random variable into equal size interval, then each equal size interval will be having the same probability. So now I write the definition of uniform continuous random variable. X is a uniform random variable if PDF of x is, say, f sub x of x, and that is equal to 1/b minus a for x greater than or equal to a and less than b. Remember, these equality, strict or loose inequalities behave the same way when it comes to continuous distributions, and obviously it is equal to 0 otherwise. What are the parameters? Obviously, there are 2 parameters. I told you in a distribution, anything other than the constants and the random variable is the parameter. So here you see b and a are the parameters. So we write where the 2 parameters are b greater than a. So if x is uniform continuous random variable, there is an equal probability of finding an outcome x in any interval of some length, and this probability will be equal to the probability of finding x in any interval of the same length. This is what we mean by a continuous uniform random variable. You simply assume that all the total interval is divided into some equal size interval, and each small interval is has the probability equal to any other interval of the same size. This is what we mean by continuously uniformly distributed random variables, and this is the PDF of a continuous uniform random variable. I'll come back to this point a little later and see why we have written it as such. You take the higher point, you take the lower point, you subtract it and divide by put it as 1 over the interval, and then you find the probability of that particular interval. Now I'll go to another theorem that will relate the CDF of a continuous uniform random variable, and I'll come back and see why we could write the PDF as such. So there is a theorem in your textbook that says if X is uniform with parameters A and B greater than A, then first the CDF of this continuous uniform random variable is 0 for X obviously less than or equal to A, which means below the first initial point. It is equal to X minus A over the total interval B minus A if X is greater than A and less than or equal to B, and it is equal to 1 for X greater than B. So this is the CDF of a continuous random variable. Now if you read this expression along with this expression, you automatically see that these two have the integral derivative relation. You know, when you differentiate the CDF, you obtain the PDF, and you can obviously see here that if you differentiate this part, the derivative here is 0, the derivative here is 0. So within this interval, the derivative of this expression is simply 1 over B minus A. So the derivative of the CDF gives you the expression for the PDF of a continuous random variable. Secondly, expected value of this X, which is a uniform random variable uniformly distributed within this particular range, is equal to B plus A over 2. Again, this is very simple. We'll see how. And third, variance of X, if X is a continuous uniform random variable, can be written as B minus A whole square over 12. Now a small homework, and that homework is you need to verify this and this using the formulas for mean and variance of continuous random variables, which I have just taught you a few minutes ago. The variance, the expectation of a continuous random variable X can be written as such, where this is the PDF. So if you use the PDF of a continuous random variable, which is this, you should be able to find how we can write the expectation of a continuous random variable as such. And similarly, you can utilize the formula of variance of a continuous random variable, the generic formula of the variance of a continuous random variable, to derive at this expression for the variance of x if x is continuously uniformly distributed. Let me do an example to improve the understanding about continuous distributions in continuous random variable distributions. So, now I have an example here about the phase angle of the signal that is input to a modem, and we say that that phase angle is given as a random variable theta, and it is uniformly distributed. So, let me first write the statement of the problem. The phase angle, call it theta, of the signal at the input to a modem is uniformly distributed between 0 and 2 pi radians. So, the angle is distributed between 0 and 2 pi radians, which means this phase angle is a uniform continuous random variable, and its value can be anything between 0 and 2 pi with an equal probability. So, you take a small interval from this range, and it has the same probability as any other interval of the same size. We need to find the CDF, the expectation and the variance of that phase angle. So, I will solve it now. This is so simple. It has already been given that the random variable is theta, and it is uniformly distributed between 0 and 2 pi. So, what is the lower value here? A is equal to 0, and here B is equal to 2 pi. So, if that is known, you can write the PDF and the CDF of this continuous uniform random variable. So, for example, if I have to write the PDF, I can write it as such: f sub theta of theta, and that is equal to 1 over b minus a, which is 2 pi minus 0, which is 1 over 2 pi, obviously, for theta greater than 0 and less than or equal to 2 pi, and it is equal to 0 otherwise. So, the probability of finding the angle, phase angle, is like this. Now, the CDF, you know how to write the CDF. It is already known to you now. This is how you write. Below 0 and above 2 pi, it is simply 0. Above 2 pi, it is equal to 1 because it is CDF. Below 0, it is 0, and within 0 and 2 pi, it is distributed cumulatively distributed in this fashion. So, the CDF f sub theta of theta is now within the meaningful range. You can write it as theta over 2 pi for theta greater than 0 and less than or equal to 2 pi, and it is equal to 1 for theta greater than or equal to 2 pi. You see the variable minus the first point divided by the total range. So it is variable minus the first point, which is 0, so theta minus 0, divided by the range, which is between 0 to 2 pi, it is simply 2 pi. So we have been able to write it as such. So this is the CDF. What about the mean value? If you see, you can utilize, you can directly utilize the formula for the expectation of a continuous uniform random variable. The last point plus the initial point divided by 2. So the last point in the interval is 2 pi plus the initial point is 0 divided by 2. So it is 2 pi by 2, so it becomes pi. And this is now so simple. You see, if you have this say 0 to 2 pi interval with the same probability, with total probability 1. So if you want to find the expected value or the average value within this range, you know that the expectation is the balancing point in a distribution. So it should lie, because of the uniform distribution, it should lie in the middle, and the middle of 0 to 2 pi is simply pi, the expected value, and hence we have been able to find this expected value, obviously in radians. For the variance, you can easily write it as such. Variance of theta should be b, if you recall, it is b minus a whole square divided by 12. So b is 2 pi, a is 0 whole square divided by 12. So it is basically pi square by 3, but in terms of radian square. You see how we can solve simple examples with reference to the continuous uniform distributions. I'll move on and now discuss the second family of continuous random variables, and that is exponential distribution. So my next topic is exponential random variable. Let me give you a quick comment on continuous uniform random variable. First, you have a feeling that all the intervals have the same probability. All the intervals of same length, if they have the same probability, then you automatically assign continuous uniform random variable to such problems. The initial important point about exponential random variables, the waiting times in general, the random waiting times are in general handled and modeled through exponential random variable. First, let me write the definition, and then I'll tell you how we can solve a few examples related to exponential distributions and the waiting times. So I say x is an exponential random variable if its PDF is f sub x of x, and that is equal to a times e raised to power minus a x. for x greater than or equal to 0 and it is equal to 0 otherwise. Where the parameter, here you see there is just one parameter and that is a, because otherwise other than this parameter it is either the constant exponent e or the variable x. So the parameter a has to be greater than 0. So you see this is something like this exponential, negative exponential, this is the PDF and this is the range of the variables. The total area under this PDF is 1, but this area becomes 1 only at infinity. Always remember this. It is negative exponential, decreasing, but converging to the total probability converging to 1, and this graph will touch this horizontal axis only at x is equal to infinity. You see how quickly the exponential distribution falls. It depends on the value of a. So the parameter a basically determines how quickly the PDF decays. So what you will take as a small homework is that you take, for example, 3, 4 different values of a and put them here and plot them on the same graph and see how a determines the drop of the plot, and then you will have the understanding on how a is responsible both here as well as here about the decline of the distribution. This is the definition. Now I'll solve a long example in a rather shorter time to give you the proper understanding of the exponential distributions, continuous exponential distributions. So the example now. Suppose we are talking about some call time, call duration in a certain phone exchange. So we say the probability that a call lasts not more than t minutes is not more than t minutes means the CDF. So the probability that a call lasts not more than t minutes is cumulatively distributed as this: 1 minus e raised to power minus t by 3. For example, for t greater than or equal to 0 and it is equal to 0 otherwise. So first we need to find the PDF, which means f sub t of t. Second, we need to find the probability that this t is greater than or equal to 2 and less than or equal to 4, which means what is the probability that the call lasts, the conversation lasts between 2 to 4 minutes. But before that, we need to find the PDF of the call duration. So this is very simple to solve. Finding the PDF is simply differentiating the CDF for a continuous random variable. So f sub t of t, the PDF of the call waiting time, is basically d ft over dt. So if you differentiate it, it will give you 1 by 3 e raised to power minus t by 3 for t greater than or equal to 0 and 0 otherwise. So now you see this is simply a continuous exponential random variable. If you recall, the general expression for the exponential random variable in the form of a PDF was a e raised to power minus ax. So now if you match it with this, it is 1 by 3, just a minute, it is a e raised to power minus ax, and here it is 1 by 3 e raised to power minus t by 3. The t is the variable and the scalar is 1 by 3. So a e raised to power minus a e raised to power minus ax, and it is 1 by 3 e raised to power minus t by 3. So we can simply and safely see that this call waiting time, call conversation time is exponentially distributed with parameter a equal to 1 by 3. Now, second part is, this is the part A. In part B, we need to find the probability that the call lasts between 2 to 4 minutes. There are two ways to find this probability. First, one, you utilize this PDF and integrate it between 2 to 4. Integrate this expression between 2 to 4, you will find some probability. Another way is you utilize this CDF and first evaluate the CDF at the higher point minus, then you evaluate the CDF at the lower point, and then you do the subtraction, you will get the same probability. So as I told you, if you have both the expression for CDF and PDF both available, it is quicker to utilize the expression for CDF to find the meaningful probability. So I'll use the same. So now the probability that t is greater than or equal to 2 and less than or equal to 4 is simply f sub t at 4 minus f sub t at 2. And so what is f sub t at 4? It is 1 minus e raised to power minus 4 by 3, which is f sub t at 4, and then minus 1 minus e raised to power minus 2 by 3. So when you evaluate it, you will get 0.25 as the probability. So with probability 0.25, the call lasts between 2 to 4 minutes. We'll move on with the concept and see how we can find the expectation and variance of this call duration. I'll extend the example and see if we can find the expected value of the call duration, expected value of the random variable t, which models the call duration time. So now we extend the example, and in part C we'll see how we can calculate the expected value of t. In part D we'll see what is the variance of the call duration. In part E we'll see how we can calculate the probability that the call is within plus minus 1 standard deviation from the average call duration. I hope you understand this C part as well. We need to find the probability that the total call time is within plus minus 1 standard deviation from the average call duration. So when time comes, I'll tell you how we can calculate this. So first we find the expected call duration, which means the average call time for this exchange with this particular CDF distribution. And the parameter A here is 1/3. So the expected value of the call can be found from minus infinity to plus infinity t times f sub t of t dt. But since the call can never start in the negative time, so your interval goes from 0 to infinity. T times what is f sub t? It is 1/3 e raised to power minus t by 3 dt. So if you solve the integral, which you have to do as part of your homework, you will see that the call duration is, the average call duration becomes 3 minutes. Now, to find the variance in the next part, to find the variance of the call duration is expectation of t square minus e square of t. You see here you have been able to find the expectation of t. You simply replace t with t square and do the integration. You will find e of t square, and then you subtract the square of this from e of t square. You will ultimately reach the variance. So you do it as homework. These are simple integrals. You will find that e of t square is 18 and e of t is again already known, 3 square. So this becomes 9 minute square. So this is the variance. If 9 minute square is the variance of t, what is standard deviation of t? It is simply 9 positive under root, and it simply becomes 3 minutes. So the variance of the call duration is 9 minutes square, the standard deviation is 3 minutes, and the average duration is also 3 minutes. So we can easily find now the last part of the example, which is the probability that the call is within plus minus 1 standard deviation from the average call duration, which means we need to find the probability that the call duration is greater than plus minus 1 standard deviation from the mean value. So the mean value is mu sub t, and the standard deviation is sigma sub t, and t is, what is the probability that t is greater than this and less than mu sub t plus sigma sub t. So this is the probability that t is greater than, what is mu t? 3. What is sigma t? 3. And less than, what is mu t? 3. And what is sigma t? Again 3. What is the call duration is plus minus 1 standard deviation from the mean value. So mean value minus 1 standard deviation and mean value plus 1 standard deviation. This is what we mean by the call is within plus minus 1 standard deviation from the average call duration. Average or the expected or the mean call duration. So basically we need to find the probability that t is greater than 0 and less than 6 minutes. So effectively we need to find the probability that the car lasts between 0 and 6 minutes. So now this is simple. It is simply f sub t at 6 minus f sub t at 0, and you already know the expression for the CDF. So you put it, you put t is equal to 6 in this expression, minus put t is equal to 0 in this expression, and you will find this particular probability. So it is 1 minus e raised to power minus 6 by 3 minus 1 minus e raised to power 0. So it will ultimately turn out to be 0.865. So this is the probability that the car lasts between 0 and 6 minutes, or in other words, the car lasts between, or the car duration time is between plus minus 1 standard deviation from the mean value. As a homework, you need to find the probability that t is greater than mu t minus 2 sigma t and less than mu t plus 2 sigma t, which is the probability that the call duration is within plus minus 2 standard deviations from the mean value. Here it will be a little tricky, but if you think, you'll see how to approach this side of the variable t. So students, we have completed lecture number 12, lecture number 2 of week number 12, where we initially discussed the concept of expected values, and then we saw how we can write the formula for the variance of a continuous random variable, and from there we went on to discuss two families of continuous random variables. First one was continuous uniform random variable, and then it was exponential, uniform exponential random variable. So continuous uniform random variable is distributed like this. You know the concept now, hopefully. It says that any interval of some length has the same probability as any other interval of the the same length. So if you, within a continuous uniform distribution, if you pick an interval, it will have the same probability as any other interval but of the same length. So this was the PDF of uniform random variable. This is the CDF of the same continuous uniform random variable, and these are the formulas for the expectations, and I have given you the homework to find the expectation and variance of a continuous uniform random variable. Utilize this PDF expression to find the basic formulas for finding these two expressions. Then we did an example of a uniformly distributed phase angle at the input of a modem, and we solved that. Later on, we moved on to the next important family, and that was the exponential random variable, and we see how it decays, it exponentially decays, and then the speed of decay depends on the value of this parameter a. So if a is greater, perhaps if a is greater, surely the exponential decays quickly, so the distribution is kind of squeezed, and if a is smaller, it is kind of a little more spread. Then we did an example of finding of the probability of a call duration. It was already given in the form of a CDF. Then we found the PDF and the probability of the call duration within this interval using this already known theorem. And then we extended the example and found the expected value of that call duration, the variance of the call duration, and the probability of some meaningful interval. For example, the call lasts within plus minus 1 standard deviation from the average duration. So average duration was found to be 3 minutes. Again, this is your homework on how to solve, how to reach this point from this point. You simply do the integration. And then you find the variance. Again, for E of t square, you have to do the integration here, but putting this t as t square. And then you ultimately find the variance and the standard deviation. And if we know all these, we can easily find this part of the problem. The probability that the call time is within plus minus 1 standard deviation from the mean value, which means mean value plus 1 standard deviation, mean value minus 1 standard deviation, which leads us to this interval. We need to find the probability of this interval, the probability that the call lasts between 0 and 6 minutes. So we utilize the CDF expression, evaluate it first at t is equal to 6, and then you evaluate it at t is equal to 0, and you find that the probability within this interval, the probability of call duration in this interval, the call duration of this length within this length is 0.865. I have given you a homework on how to find this particular probability that the call duration is within plus minus 2 standard deviations from the mean value. This part is easy, but you have to think about this part and come up with the answer. Thank you very much for your time today.